Today's tutorial is all about the chain rule. Now we've looked at the chain rule in lectures, and some of these questions are quite straightforward. For example, 45 is pretty straightforward. 46 is pretty straightforward. What I'm going to concentrate on today is probably 48 and 49 and possibly 51. Okay? Now, just for something, if you've already done all those and you're feeling bored, anyone done 55? I know the writing's really small. It's a good, anyone done it? It's a good test. I'll give you a clue how to do that near the end. So, here, 48's got three parts to it. We've defined a function of two variables in terms of this integral. Okay, so the independent variables are u and v, and then the dummy variable is t. Can anybody explain what I mean by a dummy variable? What's going to happen to that t when we integrate it, if we can integrate it? Yeah, just disappear, right? So the t, you can think of the t as just a dummy variable. So the real variables here are u and v. We're asked to write down these two partials and hence determine the derivative of this function here. Now firstly, before we do anything, notice the relationship between this and this. It's just x squared, v replaced with x squared, and u replaced with v. So that's actually going to be where we sort of put in the chain rule here. So let's have a look. Let's have a look. So I'm assuming that, all these integrals are well defined. Now we're asked to write down the partials df du and df dv. Oops, sorry. That's a v and that's a t squared. Now, what do you think will happen? Anyone done this question? Anyone? Well, it's just a fundamental theorem of calculus, right? So you're differentiating with respect to u. The u's up here, right? So all you do is you replace the dummy variable with the variable that you're differentiating with respect to and remove the integral sign. Okay? Fundamental theorem of calculus. Secondly, we're asked to calculate df dv. So that is just this. So any ideas on how we might proceed here? There's no real fundamental theorem of calculus available here. Anyone suggest what we might do? Sorry, say again? Well, yeah, essentially what we're going to do is push this inside the integral sign. And then take our partial. Okay, so if I want to differentiate with respect to v, I'm going to get something like minus 1 on v plus t squared all squared dt. Now, the point of these two derivatives is to actually tackle the more difficult part of this question. Okay, the more difficult part of this question is, what's the derivative of this function here? And like I said before, over on the right-hand side, we've just replaced v with x squared and u with x. So if this is my f of u comma v, forget about the d dx, what will this be? Well, it'll be f of x comma x squared. Okay, just by looking at the variables. So this is like the second part. So you can think of this as u and this is v. Okay, we're going to use the chain rule to calculate the derivative of g. So, u equals x, v equals x squared. Okay. We have the following. G depends on f. F, big F, depends on u and v. And u and v depend on x, because u equals x and v equals x squared. How's that? Okay, so that's our little chain rule diagram. So the chain rule gives the following. Well, we want to calculate a dg dx, so we work out all the ways from the top to an x, and when we go from letter to letter, we form a derivative. Okay, so it's going to be df du times du dx. Plus the other branch, df dv times d... Oh, sorry, that should be an x, not an x squared. Df dv times dv dx. Okay, well, we've calculated some of these derivatives up here already. And we can easily calculate du dx. Du dx is going to be 1. dv dx is going to be 2x. So let's put this all together. And we're going to get something like this. So, and I'm timesing this by 2x, so let's put the 2x in there. So all I'd like to do now is possibly do a little bit of simplification. Okay, if I want to, I can get everything in terms of x just by subbing out for the u and the v. So I'm going to get 1 on 2x squared. So plus 2x integral x0 all over v, which is x squared plus t squared squared. Okay, and so this will be 1 on 2x squared. So hopefully you can see how the chain rule can help you to differentiate these kind of integral expressions. And now, these are quite important. I didn't do one in lectures because I guess I wanted to concentrate in the tutorials. But this is quite a challenging problem, but it's at a level that I would expect you to be able to handle. Okay, it's difficult. I'll definitely give you that. It's sort of more on the upper scale. So this is above average, the difficulty associated with this problem. Okay. Shall we do another one? Okay, so 49 is basically just a repetition of 48, but with a different big F. Okay. So let's look at 49. So we're defining a function of two variables in the following way. So again, you see the v variables, the upper limit of integration, and the t variable is the dummy variable. We want to write down the partials df du and df dv. Okay, again, push the partial, or I guess the d du inside the integral sign. So now I'm differentiating the integrand with respect to u. So this is, this is a v up here. And so the cosine is going to go to negative sine. I'm going to bring a t to the front. And the 1's going to go to 0. So I'll get the following. Now I can cancel off those t's. And then all I really need to do is integrate. So I can integrate sine ut with respect to t. I'm imagining that u is a constant. So imagine u is a constant, integrate with respect to t, and I get something like this. And so if I plug in my t equals v and t equals 0, I should get something like this. All right, let's look at the other partial now, df dv. Okay, so let's differentiate this partially with respect to v. We notice the v is at the upper limit of integration. So it's a fundamental theorem of calculus. So that means we get rid of the integral sign, replace the dummy variable t with v, and just write it down. How you doing? I'm not sure if there's any more room. Yeah, so... Okay, yeah, if you want to grab a chair from next door, and yeah.
Are they meant to be this many people?
No, this is why I say subject to like room availability and seating, okay? Okay, so now, let's go back to the question. We want to calculate the derivative of this function. Again, hopefully what you should do is realise that this and this, well, we've just replaced v with x squared and u with x. So we're differentiating a function of one variable here. So I think I'll take a new page for this one. So this is 49 continued. Now this is just big F of uv with u equals x and v equals x squared. Okay, let's see if we can formulate our chain rule. We've got g equals big F. Big F depends on u and v. And u depends on x and v depends on x. So to calculate dg dx, I look at all the x's down here and I find a path from the top to an x. When I move from letter to letter, I form a derivative. So there's one path, it's df du times du dx. Plus the other path, df dv times dv dx. Now we've already calculated these two partials on the previous page. We can easily calculate these two just from here. So du dx will be 1, dv dx will be 2x. So from the previous page, I have the following. Du dx is just 1. df dv from the previous page is just the following. Is just here. All over v. dv dx is just 2x. Now let's put it all in terms of x's because I guess we're differentiating with respect to x. So let's see if we can put everything in terms of x's. So we replace u with x and v with x squared. So that'll be x cubed in there now. X squared down there times 2x. So we can cancel off one of these x's. And we're going to get something like the following when we just clean up the algebra. How's that? Can everyone see up the back? Yeah? It's probably as hard as the chain rule gets. Okay, but you can do it. You can do it. Any questions? You can do it. All right, let's have a go at 51. Anyone done 51? 51. The slightly tricky thing about 51 is that you've got second order partials. So how does the chain rule work for second order derivatives? That's the harder thing. So have they got it? Yep, good. So let's have a look and see how we go. So in 51, we've got the following. So we've got a function of two variables, and each of those variables depend on other variables. Now this is how I do an S. I know it looks a bit like a 5, but that's just the way I write. So I'm sorry for that, and sorry YouTube. So think of x and y as intermediate variables. We're asked to calculate the second order partials. So z sub r, z sub ss, and the mixed. Now I'll do one of those, or one or two of them to get you started. So let's draw our little diagram. Z depends on two things, x und y. Und x depends on two things, a und s. So it is y. So if you want to calculate, say, dz dr, we need to find all the paths down to an r. And when we go from letter to letter, we form a derivative. So there's two paths to an r, dz dx times dx dr, and the other path, dz dy times dy dr. Now to save a bit of space, I'm going to just write subscripts. So by z sub r, I mean dz dr. So what we can do now is work out all these derivatives and come up with some sort of representation for z sub r. So what's z sub x going to be? Z sub x? 2x. X sub r? 3. Z sub y? 2y. Y sub r? 1. Okay, so if I just want to clean that up, I'll get 6x plus 2y. Let's calculate z sub s. Remember, the reason why we're calculating the first derivatives is because we really want to calculate the second. Okay, so z sub s, who can tell me what's the chain rule for z sub s? I've forgotten. What is it? I want to know. Someone. Hang on, you tell me. Yeah, dz dx. Yep. And anything else? Yep. Dz dy. Yep. Good. So let's work out these partials. Again, it's going to be similar to the above in some sense. 2x times 1 plus 2y times minus 1. So we're going to get 2x minus 2y. All right, now, this is where it gets a little bit trickier because you want to find the second order partial. Has anyone done this question? Anyone know how we can... Well, how did you do it? So yeah, so you're right. Is that how you did it?
I actually subbed in right at the beginning.
Okay, all right. That may work as well. The thing is, if you don't know what these functions are, it's almost impossible to do. Okay? Yeah. Well, let's look at, instead of having a z here, let's say put a z sub r. Now z sub r will depend on a number of things. It will depend on actually the same variables. So, to get z sub rr, you just work all the way from the top down to an r. Okay? So it's going to be z sub r sub x times x sub r. Z sub r sub y times y sub r. Here we've got a function of two variables, f. We don't know what it is. We do not know what it is. All we know is that x and y have some sort of dependence on these two variables, r and theta, in a polar coordinate kind of fashion. Calculate these partials, the second order partials. So it's very similar to the one that I did before. So I'll calculate one of the second order partials and let you guys do the rest. So anyone done 52, just out of interest? Anyone? Yeah? Cool? Good? Okay, so to get the second order partials, let's do the first order partials. So drawing our little nifty diagram, we know that f depends on two variables, and each of those variables depend on two things. So the chain rule gives us the following. So let's say, let's calculate it with respect to r, dz dr. What's it going to be? df dx times dx dr. So I'm just going to write subscripts just to save a bit of space. df dy times dy dr. Now I don't know what f is, so there's no way I can calculate f sub x. I just got to leave it. But I do know what x and y, the relationship is between x and r and theta and y and r and theta. So x sub r, what's that going to be? That's going to be something like just cosine theta. Y sub r is going to be something like sine theta. Yes? So let's say I wanted to calculate z sub rr. I would draw my little diagram again. I'm not going to do z sub theta because I'm just going to leave that out. So I draw my little diagram again, just with a z sub r up the top. So z sub rr is going to be z sub r sub x times x sub r plus z sub r sub y times y sub r. Oh, I guess I can probably, yeah, I guess I can write it like that. That's okay. All right, so let's go up here and differentiate with respect to x. What am I going to get up here? Well, I'm going to, so I want to basically differentiate each of these terms with respect to x. Now, cosine theta, well, you can think of that as a constant. So f sub x differentiated with respect to x is just going to be f sub xx. And again, I can differentiate with respect to y here. So this is just that. X sub r, what's that going to be? dx dr. It's just going to be cosine theta. So what about this second term? Just repeat the process, but just differentiating with respect to y this time. So if I differentiate each of these terms with respect to y, I'll get this. And lastly, y sub r is going to just be sine theta. Now, can anyone tell me, assuming that these mixed partials are equal, I can sort of add these together. I'm going to get the same sort of terms. And I think that's a reasonable assumption to make. So these mixed partials are going to be equal. So what I can do is just simplify a little bit. So I'll take a cos squared out there, and I can expand that and get 2 f sub xy cos theta sine theta, and then the last one's going to be something like sine squared theta f sub y. So the other cases are similar, and I'm going to leave them for you to do. Questions? Questions? You guys can do it. Yes?
Is like the second diagram for the sub r
Yep.
going to be dependent on the same variable as z?
Yes. Yep. So that's something that you can use, assume all the time. Okay, so you just you're keeping the same dependence, you're just changing the original type of function. So what this says is that we're only considering functions where this is true for some m. Okay? So m might be 2 or 3 or something. We don't know what it is. So we can think of just m as being sort of fixed, but I guess it's fixed and positive. Okay. Now, we want to show under certain conditions that x times f sub x plus y f sub y equals m times f. That's what we want to show. Okay, now I'm only sort of hinting for B here, I guess really. Any ideas on how to start this problem? We've got some information here. We want to prove this. I guess. Oh, what? Sorry, someone said something over there. Say again. With respect to t, yeah, excellent. How did you think of that? I think it's great. Well, firstly, look. I think it's great. Look in the thing we want to prove. There's no t's in here. Okay, there's t's up here, but no t's down here. There's an m up here and an m here, but there's no. There's no sort of explicit t. So so my hint is the following. Think of u as being t times x. And so we're introducing these sort of intermediate variables. And v as being t times y. Differentiate both sides of star with respect to t by using the chain rule. I mean, you don't have to use the chain rule over here, of course. If you differentiate with respect to t over here, you're just going to get m times t to the m minus 1 times f. Okay? So the right-hand side is going to give you something like m times t to the m minus 1 times all of this. And the left-hand side will give you something else when you differentiate. Now, if I set t equal 1, I'll get this on the right-hand side, and I'll also get this. Okay, so it's a two-step process. Differentiate both sides with respect to t. You need to use the chain rule on the left-hand side, just regular differentiation on the right-hand side, and then plug in t equals 1. You will get that.